Now let's look at one more example where an object has an initial velocity at an angle. A ball is launched from the ground with a velocity of 22 meters per second at an angle of 63 degrees. If the angle isn't described relative to the vertical or some other line, we'll assume it's 63 degrees above the horizontal or above the ground. For this example, we'll place the origin right at the starting point of the ball, so the initial x and y positions are both 0. How is the ball being launched from the ground? Like we said before, that doesn't really matter for projectile motion. We just care about the initial height and the initial velocity. We could say the ball was kicked into the air, or maybe it was shot out of a cannon below ground level. The point of a setup like this is that the initial and final heights are both 0. Next, what do we do with this velocity vector? In pretty much every case, we need to find the components, the initial x velocity and the initial y velocity. Remember, a vector and its components form a right triangle, so we can use the right triangle trig relationships. The initial x velocity is the initial velocity times the cosine of this angle, which is 10 meters per second. The initial y velocity is the initial velocity times the sine of this angle, which is 19.6 meters per second. Cosine and sine don't always go with x and y. Just remember that cosine is for the component adjacent to the angle we're using, and sine is the component opposite from the angle. So these are the initial x and y velocities. When the ball is launched, its actual velocity is 22 meters per second in this direction, but it's moving up at 19.6 meters per second, and it's moving to the right at 10 meters per second at this initial time. Now we have all the initial values. So what does this motion look like? What's happening to the x and y positions over time? What about the x and y velocities? Is there anything about this that's similar to the last example? Here's the ball's position at half-second intervals. The ball moves up, reaches a maximum height, and then falls down. And it's moving to the right the whole time. If we look at the horizontal motion, the ball moves the same distance to the right during each interval. Just like before, the x velocity is constant because there's no acceleration in this direction. The ball is moving 10 meters per second to the right the whole time, so the ball moves the same amount each second. It's the same motion as a ball rolling on the ground at 10 meters per second. It doesn't matter what's happening in the vertical direction, the horizontal motion will always be the same. Now let's look at the vertical motion during the period when the ball is moving up. The distance between each height is getting shorter over time. Why is that? Gravity is acting downwards, in the opposite direction as the velocity. If the velocity is positive and the acceleration is negative, the velocity will decrease over time, and the ball slows down in the vertical direction. So the ball moves less vertical distance during each interval. Then the ball reaches a maximum height and falls back down. As the ball falls, the y velocity increases, and the ball falls a greater distance during each interval, just like we saw in the first example. So for the first half, the ball moves up, but it slows down in the y direction. During the second half, the ball falls down and moves faster in the y direction. Notice that the height of the ball is the same at equal times before and after the maximum height. Half a second before and after, it's at this height. 1 second before and after, it's at this height. Since the initial and final heights are the same, this trajectory is symmetric. The ball takes 2 seconds to move up and 2 seconds to fall down. Also, notice that this is the same vertical motion as a ball that's launched upwards at 19.6 meters per second. Just like with 1D projectile motion, when the ball reaches the maximum height, the y velocity is 0 because it's reversing direction. The ball is still moving to the right, but it's not moving up or down at that moment. So the horizontal velocity is constant, but the y velocity changes because of the acceleration due to gravity. If we combine the x and y velocity components at each time point, we can see the actual velocity vector of the ball. The x components stay the same, but the y component changes, which changes the length and direction of the vector. The vector always points in the direction of the ball's motion, and when the ball is at the maximum height, the y velocity component is 0, so the velocity is just the x velocity. If we line up the vectors at each time, we get a different view of how the velocity vector is changing. The x velocity stays the same, but the y velocity starts pointing up, then gets shorter until it's 0. Then it flips and gets longer in the negative direction. So the vector changes length and it rotates. Now let's quickly run through the actual values of the positions and velocities. Then we can look at the motion graphs for this example. Let's start with the x motion. We can use this equation to find the x position at each time point like before. We plug in 0 meters for the initial x position, 10 meters per second for the x velocity, and the times to get the x positions. The x velocity is constant, so the ball moves 5 meters during each half-second interval. Here's the graph of the x position versus time. It starts at 0 meters and increases with a constant slope, which is the velocity. Since the x velocity is constant, it's always the same as the initial x velocity, 10 meters per second. If we graph that, it's just a flat line. Here's the position, velocity, and acceleration graphs for the x motion. The position goes from 0 meters to 40 meters, the velocity is always 10 meters per second, and the acceleration is 0. These are the same graphs that we'd have for a ball rolling on the ground at 10 meters per second, since we're only looking at the motion in the x direction. Now let's look at the y motion. We can use this equation to find the y position at each time. The initial y position is 0 meters, the initial y velocity is 19.6 meters per second, and the y acceleration is negative 9.8 meters per second squared. When we plug in each time, we get the y positions. Notice how the y position increases from 0 to 2 seconds, then it decreases. We don't need to calculate the up and down motions separately. This equation covers the entire vertical motion. The initial velocity is positive, and the acceleration is negative, and that's how the math works out. Here's the graph of the y position versus time. It starts and ends at 0 meters, and it reaches a maximum height of 19.6 meters at 2 seconds. This graph looks like the two-dimensional path of the ball, but it's not. It's just showing us the y position over time. This is the same graph as a ball that's launched directly upwards with the same initial y velocity. We can find the y velocity at each time using this equation. The initial y velocity is 19.6 meters per second, and the y acceleration is negative 9.8 meters per second squared. Notice how the velocity starts at positive 19.6, it decreases to 0 at 2 seconds, then it becomes negative and increases in magnitude. Again, this is how the equation works. The initial velocity is positive, and we subtract from it each second because the acceleration is negative. Here's the graph of the y velocity versus time. It starts at 19.6 meters per second and ends at negative 19.6 meters per second. It has a negative slope, which is the acceleration. And this is the same velocity graph as a ball launched directly upwards. The velocity starts out positive, it slows down to 0 at the maximum height at 2 seconds, then it becomes negative as the ball falls down. And the velocity has the same magnitude at equal heights, except the direction is flipped. Here's all the graphs for the y motion. The slope of the position graph is the velocity, so the position starts with a positive slope, the slope decreases to 0, then it increases in the negative direction. So how does this motion compare to the first example? In that example, the ball started at some height with a horizontal velocity. That motion is just the second half of this motion. It just starts 2 seconds later when the ball is at the maximum height. The x velocity is 10 meters per second and the y velocity is 0. They both take 2 seconds to fall from the maximum height to the ground. Here's the x and y positions and velocities for the second example. If we start the clock 2 seconds later, we get the values for the first example. If we start with the y motion graphs from the second example, and we shift them 2 seconds to the left, we get the graphs from the first example. So the ball starts at a height of 19.6 meters and a y velocity of 0. And the same is true for the x motion graphs. The x velocities are the same, but in the first example, the ball is in the air for half the time, so it only travels half as far before hitting the ground. Now let's wrap up this example by finding the speed of the ball when it lands. Just like the first example, the final velocity vector is the combination of the final x velocity and the final y velocity. We know the final x velocity, so let's find the final y velocity using this equation. We plug in 19.6 meters per second for the initial y velocity, negative 9.8 meters per second squared for the y acceleration, 0 meters for the initial y position, and 0 meters for the final y position when it hits the ground. Since the initial and final y positions are the same, the terms on the right are multiplied by 0. The final y velocity squared is equal to 19.6 squared, so the final y velocity is 19.6 meters per second. Again, this equation actually gives us the speed because v is squared. The final y velocity is negative 19.6 meters per second, since it points downwards. Now that we have the final x and y velocities, we can use the Pythagorean theorem to find the speed, which is the magnitude of the final velocity vector. When we do that, we get 22 meters per second for the final speed of the ball. This is the same as the initial speed when the ball is launched. That's because the initial and final heights are the same, and the trajectory is symmetric. So we could have just answered this question by remembering that concept.